start recording this, huh? So, ionic radius increases, decreases. Ionization energy decreases, increases, because they have a what relationship? Inverse relationship. Good. Okay, so today is 12/9/15. Break is coming, folks. The light at the end of the tunnel is not a train. It is a week of doing your own thing. Okay. We left off talking about what cations and anions are and how to remember that. And we were just about to talk about how forming an ion changes the radius. So I'm going to draw one of those little ringy radius things. I'm going to do something really simple like, whoops, lithium. So this is lithium. Here's a neutral atom of lithium. It's got 3 protons. Neutral atom of lithium has how many electrons? 3. That was easy, Moser. Okay. And they're arranged like that. So I've got 2 on the inner shell, and I've got 1 on that outermost energy level. If we remove this out, so right now, let's think about it in terms of tug of war. How many of you have ever been involved in a game of tug of war? Okay, good. I don't have to assign homework. So right now, in terms of attraction and in terms of radius, we have 3 protons engaged in a tug of war with 3 electrons. I'm going to shrink that. Okay. So it's a fair fight. You know, and we've got all the considerations about electron shielding and all that stuff that affect the radius, but we've got 3 on 3 for the tug of war. If we create a lithium ion, so I'm going to copy this whole, whoops, undo. Copy, paste. If we create a lithium ion, how would we do that? How would lithium become an ion? It would lose an electron to be just like helium, the cool noble gas in the period above it. So we cut this out. We now have lithium 1+. And what does that tug of war look like at this point? We have 3 protons exerting a force on how many electrons? 2. You know, so in this case, we also just lost, an energy level, but more importantly, this is suddenly no longer a fair fight. And so the radius of this whole thing contracts. You know, now in this case, like I said, it also lost an energy level. So not only do we have that happening, but we have that happening. So the radius of the lithium ion is going to be smaller than the radius of a neutral lithium atom. Well, what if I have, let me copy just this. What if I have a slightly different situation and I make an anion? So we're going to deal with, whoops, actually I could have skipped that, huh? Cut. We're going to deal with fluorine. So here we have a neutral atom of fluorine. It's got, and I'm just going to put 9 protons. And then its electron arrangement, it's got 2 on the inner level, and then 1, 2, 3, 4, 5. I really should make these a different color, shouldn't I? There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's got 9 electrons. Okay? So there's a neutral atom of fluorine. How would fluorine become an ion? What would it do? Gain or lose? how would fluorine become an electron? Or, I'm sorry, become an ion? Is it going to lose an electron? It's going to gain one electron because it's one electron away from being like a noble gas. If it adds an electron, it's just like the next group. It's just like the noble gases. And I'll put in the extra electron that we get in a different color. They're all the same. All electrons are the same, but that helps. So, whoops, let me actually copy this whole thing. So we gain an electron, and now we have fluorine 1+. Well, over here, for tug of war, we had 9 protons pulling on 9 electrons. Fair fight. What happens when we form an anion? What happens to that sort of tug of war? We now have 9 protons exerting force on, 10 electrons. No longer a fair fight, but instead of the radius contracting, now the radius expands a little bit because those 9 protons had a grip on all 9 electrons, in essence. Well, now they've got one more to watch. They've got one more to pull in. And the electron cloud actually expands a little bit. So we see when we form an anion, the radius actually increases. So you form a cation, the radius goes, it squeezes in a little bit. You form an anion, it actually expands. It puffs up a little bit because the nucleus cannot exert the same kind of charge it did when it had fewer electrons to manage. Questions on that? Okay, so this is a multi-part game. I'm going to name an element. You write down the following. So here, we'll do an example together. So I'm going to say calcium. You write down what ion calcium would form and whether it would have a larger or smaller radius than its neutral counterpart. So for calcium, we'd say, oh, well, calcium, it's in group 2. It's got 2 valence electrons. To be like argon, it has to lose those 2 valence electrons. So it forms calcium 2+. If it forms a cation, its radius does what? Oh, it decreases. Can you do that? Okay. We'll practice it. So let me give you aluminum. Aluminum. Go. Oxygen. What does oxygen do? Somebody wearing red, orange, or yellow? Ooh, Caitlin? This never happens. You might. Well, okay. We'll count Madison too. So Caitlin or Madison. We'll count Destiny for the. Oh, there's some red on everybody. I knew that. I'm sorry. I knew that. Okay. So Caitlin or Kenzie or Destiny. And we could probably count Laurel. Oh, you've got a red shirt on. How did I miss that? Okay. Who wants to take it? What does oxygen do? 2-. Okay, 2-. Do you agree? Yeah, that's typical for oxygen. So does its radius increase or decrease? Increases. Okay. Questions on that? Do you feel fairly comfortable with that?
Whenever you're looking at, does the element just do what's easiest to get to the state to be a noble gas?
Yes. So, and we're going to talk about this extensively. But I'll say it now. I mean, I don't mind saying this one 40 million times. So on that uppermost occupied energy level, you basically end up with between 1 and 8 electrons. If you've got 1, 2, or 3, it's easier to give them up. It takes less energy to give them up than to add. If you've got 5, 6, or 7, it's easier to add electrons to get to 8, because they're all trying to get to 8. They're trying to get to that full S&P. 4 is the weird ones. 4 are really the strange ones. Things with 4 valence electrons most commonly bond covalently. They most commonly share. They can form ions, and they kind of can go either way. They can lose or gain, though most of them have a typical behavior where, you know, oh, they usually do this. Carbon has 4 valence electrons. Carbon can form 4 points of attachment covalently. But there are compounds that are carbon ions. So if you've ever heard of like a carbide, tungsten carbide blades, or tungsten carbide drill tips, that is an ionic compound formed from tungsten ions and carbide ions, which is a negative carbon ion, carbon that's added 4 electrons. So it happens. But you know, the general rule of thumb is 1, 2, or 3, you're going to lose. 4, 5, or 6, you gain. 4 are the weirdos. You know, they most commonly share, but they can lose or gain, and it's just kind of case by case. So that's one of those concepts that you just have to know. That is so foundational to everything we do pretty much for the rest of the year. Looking at an element, looking at where it's at on the periodic table, and being able to say, oh, that's going to form a 2+ ion. Oh, that'll form a 3- ion. That's really foundational. Yes, ma'am? Okay, so you've got one more trend, and it's not so, well, this, let's disregard that. You've got one more sort of trend. It's not necessarily, well, yeah, we could look at this in lining it up with the periodic table. How would you do that? So as you go across a period, since that's how we're thinking, as you go across a period up to about here, ion formation tends to result in what kind of change in radius? An decrease in radius, yeah, because those tend to form positive ions. From here over ion, well, of course we don't count the noble gases there. From here over, ion formation tends to result in what kind of change in radius? A decrease, because those tend to form negative ions. Okay, so I mean, I guess you can line that up periodically. Okay, let's talk about valence electrons. So that was a fantastic question. I don't even remember who asked that now. That's how short my short-term memory is. Who are you? Why are we here? Hi, Noel. So valence electrons. This is the piece. And have I given you the ladder talk lately? Or the we're on a road climbing up a hill talk lately? Okay. Chemistry, more than anything else I have ever taught in my life, is a ladder. I love chemistry for that reason. I didn't want to teach chemistry. I didn't set out to teach chemistry. I love teaching chemistry. It is such a building process. So you already, we're in chapter 5, you already have skills you didn't have on day 1 coming in. And every single day, if you're doing what you're supposed to be doing, you're building a new skill. And if you build that skill well, the next day you stand on that rung of the ladder that you're building. And if you don't make good rungs, then by about 3/4 of the way through the year, you just fall off the ladder. And I'll try to keep pushing you up. But you gotta be building the ladder. And I gotta say, I'll pause this. When I talk about the ladder thing, and this was probably like the second time I ever taught chemistry, and I think at that point I didn't fully understand what a ladder building process it was. So, you know, we talked about all this stuff, but I didn't keep stressing, like, this you have to know. And we got like 3/4 of the way through the year, and I had one person who, every time I would say, like, okay, calcium, what kind of ion is that going to form? And this person would say, I don't know how you people know that. I don't know where you get that. Oh my gosh, you can't do anything else. You're stuck. You didn't build that basic skill. You are stuck. So this is really foundational. just looking at the periodic table and knowing automatically how many valence electrons there are for an element. So the simple, stupid cheater formula is this. Group 1 and 2, it's the number of the group. Group 1 has how many valence electrons? 1. Who's buried in Grant's tomb? Grant. Group 2 has how many valence electrons? 2. Who's buried in Grant's tomb? Still Grant. For 13 through 18, it's group number minus 10. So group 13 has 3. Group 14 has 4. You get the drift. All the way up to 18, they have 8 valence electrons. Those are your noble gases. Okay? We really only use those kind of rules for valence electrons for what we call the main group elements. And remember, the main group elements are which blocks? S and P. The reason being, and I always do that, the rules are a little bit different. It gets a little bit weirder with the D block. And if you've been working on the homework, you've noticed there's the question about the usual configuration for each group in the D block. And it's kind of weird because you have that crossover. You're always filling one behind the highest occupied man energy level. So we don't talk about valence electrons the same way for the transition metals. The concept of valence electrons is most clearly applied to the main group, so S and P. And you just got to know that. So on the test, a very fair game is, here's a periodic table. What ion would sulfur be likely to form? How many valence electrons does sulfur have? Will sulfur lose or gain? How many? And there are some questions in your homework that are like that. Because in the next chapter, we're going to start building compounds. We're going to start bonding and looking at how substances bond, and then we start naming, and it starts to roll from here. You're building a chemical vocabulary, and this is one of the low rungs on that skill ladder. Okay. Speaking of the D block, well, actually, let's talk about electronegativity first. Okay. So, I believe I have mentioned my love of chocolate chip cookies and my utter hatred of raisins. Have I not? Once or twice? Yeah, I know. I feel strongly. Electronegativity. This is how much a particular atom loves the electrons. And remember, I have to say it, it's a metaphor. Atoms don't love anything. They don't have brains. They're not sentient beings. It's a matter of how strongly an atom can attract something, how it can attract electrons. And we only talk about electronegativity in the context of bonded atoms, because it's how strongly it attracts the electrons when they're sharing them. So, to pull out the raisin cookie metaphor again, if you and I, does anybody here just love oatmeal raisin cookies, like thinks they're the most awesome thing in the world? Okay. You and my mother. My mom loves oatmeal raisin cookies. Now, when I was growing up, she left out the raisins because she's really nice. But okay, if you and I are sharing a plate of oatmeal raisin cookies, you can have them really close to you. That's fine. Because I don't really like them. We're not going to have to fight over those. Now, you like chocolate chip cookies as well? Who doesn't like chocolate chip cookies? Nobody doesn't like chocolate. Oh, okay. Well, some people don't like chocolate chip cookies. If we're sharing a plate of chocolate chip cookies, they're going to have to be in the middle, dear, because I'm going to want some of those. So don't you move those any further. I want some. Nope, it stays right there. Because we have an approximately equal attraction for chocolate chip cookies. We have a very uneven attraction for oatmeal raisin cookies. You can have them all. Atoms do something similar with their electron clouds. So we're going to, we've been drawing atoms with little concentric rings. We've been drawing all that stuff. I'm going to draw what I call the big blobby atoms. So let's look at, well, that's a bad example. Nitrogen and oxygen. Okay. No. Get it? So nitrogen and oxygen form a whole bunch of compounds. We have nitrogen dioxide, dinitrogen trioxide, all these different compounds form between nitrogen and oxygen. And each of them going into this, let's move the oxygen a little bit further away. This is what I love about doing the notes on here, is you can actually move stuff. Going into it, they each have an electron cloud. They bond by sharing electrons. So what they do is their electron clouds actually overlap. And they sort of fuse into one shared cloud. Well, the thing is, oxygen is more attractive to electrons. Oxygen is better able to pull electrons towards it than nitrogen is. So instead of them sharing that cloud evenly, and I'm going to actually redraw the cloud, what ends up happening is that oxygen gets more of the cloud. Okay? Oxygen gets more of the cloud. If you have ever, as a kid, gotten shoved into a big bed with a bunch of siblings, cousins, friends at a sleepover, or whatever, you know somebody's always a blanket hog? It's analogous to that. Oxygen pulls the blankets off of nitrogen. Blankets being the electron cloud. It's a metaphor. There are no blankets. We all know this, but I just have to keep stating it. Oxygen is more able to pull that electron cloud towards itself because it is more, wait for it, electronegative. So electronegativity is the ability of an atom to hold the electron cloud when they're in a compound. It's really just, it's a measurement of how unevenly they share. Okay? And if we look at this periodically, because that's what we're doing, if we look at this on the periodic table, electronegativity tends to increase. So En increases as we go across a period. The group trend is not as clear. It usually either decreases as we go down a group or it stays about the same. So in some groups, we could say like, oh, the electronegativity for group blah, blah, blah is right around this. And it's pretty similar in all members of the group. In some groups, there's a marked decrease. So electronegativity tends to, En decreases as we go down. So based on that, where would you expect the most electronegative, where would you expect the most electronegative, the most electronegative elements to be? Circle it on your periodic table. Where would you expect the most electronegative elements to be? Okay, so I'll start recording it. A lot of people have said, well, if that's the case, helium should be the most electronegative. And that is a fantastic guess because that follows the trends. What's the problem with that? Huh? It is related to the fact that it's a noble gas. What's the problem with that? It doesn't form compounds. And we can only measure electronegativity in the context of bonded atoms. Actually, the single most electronegative element there is fluorine. Okay? And remember that hydrogen shouldn't really be there. That's just sort of an anomaly of the Van Brainer table. Fluorine is the most electronegative element there is. Fluorine is a gigantic electron hog. It will strip electrons off your grandmother. You know, it is, to use a metaphor again. Okay. Let's talk briefly, and this is the last thing we're going to talk about. That D block, those oddballs. Well, first I should ask, any questions about electronegativity? About all the trends we've looked at, they all, if you put them together, kind of make sense. You know, radius decreases as we go towards fluorine. Oh, because they're holding electrons more tightly. Electronegativity increases as we go towards fluorine. Oh, because they're holding electrons more tightly. Ionization energy increases as we go towards fluorine. Oh, because they're holding electrons more closely. Like it all, if you look at all of them together, it really kind of makes a coherent pattern. I see a crinkled brow. Is that a question? Okay. Sometimes brows just are crinkled. Sometimes they're questions. I like to check. Okay, so the D block and the F block. The D block is fairly homogeneous. They're pretty similar. They're referred to as the transition metals, of course. You've heard that term a lot. And they're more like one another than not like one another. So they are classically metallic. They are shiny. They are conductive. They are malleable, ductile, all that stuff. Varying levels of reactivity. Like we said, copper will react with atmospheric water, with the oxygen in atmospheric water. Gold doesn't react. It's very unreactive for a metal. So they're more like one another than not. Ion formation. So because remember these things are existing on that crossover, and ion formation is, we talk about it being sort of the basis for bonding. Let's look at one of the D block elements. Whoops, that's not the slide I want. Okay, let's look at iron. So noble gas notation for iron, argon plus 4s2, 3d, 1, 2, 3, 4, 5, 6, 3d6. So we're accustomed to thinking that the electrons on the highest occupied main energy level are the ones that participate in bonding. But what happens in the D block and the F block, because the highest main occupied energy level is not the highest energy level here, or it's not the highest subshell. 3D is higher energy than 4s. That's why 4s fills first. So in the D and F block, electrons come out of the highest energy orbitals first. It's like a last in, first out kind of thing. The last electron that you added is the first one to come off. So that's why we don't talk about valence in the same way with D and F block. And because of the fact that they do this weird last in, first out, it's not the highest energy level, very often the transition metals will form multiple ions. So when you look at the D block especially, you'll see that sometimes things switch over from an S to a D, and it's not lined up exactly perfectly according to the rules. They're a little bit weird. And so like iron, for instance, can form a iron 2 or iron 3 cation. It does either. It doesn't form a 6. Basically, all of the stuff that appears after the noble gas is capable of participating on bonding, and in the next chapter we're going to talk a lot about delocalized electrons in metals. Okay, that, friends, is it. That is it for the Chapter 5 notes. I'm going to give you time to work on homework. By now we've covered all the concepts that are represented there. So homework is due tomorrow. We're going to do a test on Friday. So I can give you I'm going to give you a FIP quiz tomorrow as well. So, which will kind of be like a practice for the workout. You've had one FIP quiz, but I want to give you some more practice with the concepts. And we'll start bonding on Monday. Aw, bonding. Never mind.